Hello everyone, welcome to my final presentation for my final year project titled Design Circuit of Energy Harvesting System Transducer. My name is Muhammad Rashid Rida bin Muhammad Firhat and my supervisor is Dr. Shukri bin Mat Ali. The contents that I will be presenting today are Introduction, Literature Review, Methodology, Results and Discussion, and also conclusion and further recommendations. So let's get started. Nowadays, fossil fuels still remain as the main source of energy to power our cities. The usage of these fossil fuels is bad for our planet and has led to environmental problems that we face today, such as global warming and rising sea levels. Therefore, it is important that we depend more on renewable energy. The future looks promising though, as the world is slowly progressing towards that direction. Since 2011, renewable energy has been growing faster than any other forms of energy. However, we are still far from done, as it is important that we find out varieties of ways to harvest, use and manage renewable energy with more efficiency, so that unnecessary loss can be prevented. Furthermore, with the world moving towards IR 4.0, we see an increase towards the production and usage of IoT devices. Current IoT devices such as smartphones and wireless sensor nodes uses electrochemical batteries which have limited lifespan. Despite the technological advancements made to improve the battery life of these devices, replacement or charging is still needed, and this is especially taxing for IoT devices located in difficult to reach places, while also increasing the cost for maintenance. Energy harvesting from natural resource is a more cost-efficient option for these devices. The solution that we are aiming for is to make an energy harvesting device that can harness energy from flow-induced vibrations. What is flow-induced vibrations? When water or wind flows over an object, vortices formed around the object causes it to vibrate. The mechanical vibrations caused from this phenomenon usually remain unused and wasted to the environment. Therefore, the device that this research proposes aims to convert the wasted mechanical vibrations to electrical energy capable of powering IoT devices. To achieve this, the energy harvesting device is designed to be small-scaled and portable, while also equipped with the function to connect with other units and combine the converted electricity to power other bigger devices. This research focuses on the design of transducer circuit for the energy harvesting device. In order to get the maximum efficiency of energy conversion from flow-induced vibrations, understanding of the phenomenon, which is flow-induced vibrations, careful consideration of method of energy transduction, as well as good circuit design and choice of components and materials are necessary. These are the aims of our research. There have been several studies proposing different transduction methods such as piezoelectricity, electromagnetic, and electrostatic. Our desired method of transduction is piezoelectricity. Because of its high energy and power density, simple structure can be fabricated at micro and macro scale, and its ease of application, as according to Kovaci and Conti. In the picture below, you can see a research done by Ashwati using an array of circular piezos to convert pressure to electricity. Piezoelectricity is defined as electric charges that accumulate in response to applied mechanical stress in materials that have non-centrosymmetric crystal structures, as according to Briscoe and Dunn. Piezoelectricity is a form of coupling between mechanical and electrical behaviors of ceramics and crystals belonging to certain classes, as according to Ertug and Inman. In the diagram, you can see that when piezoelectric materials are compressed, electricity can be produced. There are several types of piezoelectric transducers that can be used in varieties of applications, such as circular piezoelectric cantilever, stack, and cymbal. For this circuit, we used a film piezoelectric sensor LDT128K. These are the specifications. To test the capability of the transducer circuit, a model of the energy harvesting device is designed and fabricated. The second picture shows the mechanism of the transducer. The piezoelectric sensor is placed on top of a plastic film connected to the sliders. When the cylinder vibrates, the piezo will experience bending, thus producing electricity. An experiment was conducted to find the energy harvested depending on the characteristic of vibration. This is a diagram of the experimental setup showing an ultrasonic sensor and a piezoelectric film sensor connected to an Arduino board. An ultrasonic sensor is used to measure the amplitude of the vibration, while the data of voltage is obtained from the piezoelectric sensor. Now I will explain the process of data analysis. Firstly, the experiment was conducted where the cylinder is manually oscillated at controlled variables, varying the amplitude and frequency of the vibration. Next, the values of voltage and amplitude can be monitored in the Arduino serial monitor. After that, the data is imported into MATLAB, where a series of calculations is run to find the signal power spectral density graph and the VRMS value. From the VRMS value obtained from MATLAB, we can finally calculate the average power using formula. The first figure shows the graph of normalized values of amplitude and voltage versus time for y divided by d equals to 0.5 at 2 Hz of frequency. This data was extracted from Arduino serial monitor and recorded in Excel, where the graph is plotted. The second graph is plotted in MATLAB, shows the power spectral density graph, which estimates the dominant frequency present in the voltage signal. This ensures the validity of the experiment that the cylinder was oscillated at the desired frequency. The third graph shows a voltage versus time graph plotted in MATLAB, as well as a calculated value of VRMS. The results of the experiment are shown in this graph. The graph shows the power produced by y divided by d values of 0.5, 0.25 and 0.1 at frequencies of 1, 2 and 4 Hz. From the experiment, we can see that the power produced from the circuit is largely impacted by the amplitude of the vibration. Increasing the amplitude and frequency also increases the power output. Based on the experiment, the highest average power obtained was 0.01199 microwatts for each oscillation at y divided by d values of 0.5 and 4 Hz of frequency. Further testing was done, including a capacitor to the circuit. This graph shows the voltage accumulated versus time. In 60 seconds, at vibration characteristics of y divided by d equal to 0.5 and 4 Hz of frequency, the circuit was able to charge a 22 microfarad capacitor up to 0.14 volts. In conclusion, for a small-scale device, the best method of transduction is piezoelectricity due to its high efficiency and ease of application. The type of piezoelectric transducer used is a film piezoelectric sensor LDT1-028K, capable of producing an average power of 0.01199 microwatts at y divided by d value of 0.5 and 4 Hz of vibration when applied to the fabricated model. The results show that the average power increases as the amplitude and frequency of the vibration is increased. Some future recommendations that I would like to suggest are to increase the number of piezoelectric sensors in one system. Secondly, to optimize the mass spring system so that it can achieve the galloping phenomenon. And lastly is better application of piezoelectric sensor for optimum efficiency, such as the placement. And that's all from me. Thank you for listening.